So what do these movies all have in common?
Well, at least we can all agree the third one's always the worst.
Yeah, pretty much that. The third movie in a trilogy tends to be the worst. But thankfully, this lecture series isn't like a movie trilogy, it's more like a TV show, Season X of Your Life in Chemistry. Today there will not be a recap because we're starting a brand new section. In fact, we're finally getting into chemistry. Today we will discuss equilibrium, which you've learned about before, but I'll probably go into some details that you haven't heard before, and it's probably been a while anyways. And we really need to understand this to launch into our first major AChem topic that will take several lectures to cover. So imagine that we have a vessel that contains H2 gas and I2 gas. And these gas particles are moving around and colliding with each other. And every now and then, that collision might have enough energy where a reaction can take place, and the hydrogen and an iodine swap places, and we produce two HI gas molecules as a result. Some time would pass, and we would begin to accumulate an appreciable amount of this HI product. More time passes, and we'll accumulate even more product. And as we're accumulating product, we are, of course, running out of reactants. And the thing that's going to start to happen is, we'll have enough products that they'll start colliding with each other with an appreciable frequency, and sometimes those collisions will cause the reaction to go backwards. In other words, two HIs will reform the original H2 and I2. And as we accumulate more HI as time goes on, this reaction of two HIs with each other will get faster and faster and faster. At the same time, as we've continued to lose reactant, this reaction here will slow down. Eventually, as this reaction slows down and this one speeds up, the two reactions will finally start going at the same pace. And that is what we call equilibrium. At that point, nothing will change anymore. Now, it's not so much that nothing is changing, it's just that changes are happening in both directions at the same speed. So maybe 100 products are formed in 1 second by that forward reaction. But in that same second, 100 products are used up by that reverse reaction. So there's no net change in anything. But that's why we call it a dynamic equilibrium. Dynamic to emphasize that things are still happening, it's just that effectively nothing is really changing. And so to attempt to give more of a visual demonstration of what I'm describing, imagine at first you have nothing but reactants, and so the only reaction that can occur is that forward reaction. And it occurs at maximum speed possible. But then as we lose reactant, it slows down. On the other hand, no pun intended, at first nothing happens because we have no product, so there is no reverse reaction. But as we accumulate product, it starts to go. As we get more product, it goes faster and faster until the two meet somewhere in the middle. And to try to do both these things simultaneously is difficult, but let's give it a shot. What am I doing with my life? It's probably as good as it's going to get. But hopefully you can just get the idea of what's happening here and why it's important. One more time, equilibrium means that both reactions are still happening, but they're happening at the same speed, somewhere in between nothing and maximum speed forward. And so at equilibrium, these concentrations are no longer changing. Now sometimes these concentrations that we start with are basically zero and everything's turned into product because that forward reaction is just so much more favored than that reverse reaction. And in those cases, rather than use this equilibrium arrow, we would just draw a forward arrow to represent that the reaction's effectively going to completion, and this is what you're used to seeing at the start of a Gen Chem class before you eventually learn about equilibrium. But when we have that more equilibrium-like situation, we'll have some reactants and some products all in appreciable concentrations. And their concentrations relative to one another can be described by this thing called the equilibrium constant, or K. So let's talk about K, this thing called the equilibrium constant. And let's just use some generic reaction, no actual chemicals. We'll just say that we have two chemicals reacting that we'll label A and B, and we'll say that they produce C and D, and then as C and D accumulate, they start to react backwards, and eventually equilibrium is reached. Now let's say the coefficients for each of these species is just lowercase a, b, c, and d. So this thing called the K expression is going to describe the relative concentrations of all of those species when we have reached the state of equilibrium. And the way we set it up is as follows. K is equal to, and it's going to be like a fraction, and what we're going to do is write the concentrations of our products on top, so C times D, and then we'll write the concentrations of our reactants on the bottom. Concentration of A times the concentration of B. Now some of you who remember this are thinking there's something missing, and that would be the exponents. And the exponents that go with each of these concentrations are just whatever the coefficient is with respect to that chemical species. Why this is how the expression is set up is more of a PChem idea. We just need to understand how to set up the expression and eventually understand what it tells us and how we use it, but that comes later. Right now we're just learning basic theory. And so let me make a couple more points about K. First, let's address what the units are based on what state the matter is in. So state and units, we'll make a quick little table. When the state of matter is aqueous, again that means dissolved in water, then the appropriate unit in this class is molarity, or capital M. If the state of matter is a gas, then the appropriate unit of concentration is actually pressure. Specifically, we use the bar unit of pressure, although in Gen Chem you very well may have learned it's ATM, or atmosphere. But these are the units that we would use for literature values. Units for literature, quote unquote. In other words, if you were to look in an actual legitimate research journal for the values of K, unless they specified otherwise, these would be our default units that go into that K expression. Now as for solids and liquids, well, they just don't go into the K expression, so we'll just say not in K. So it doesn't really matter what their units would be. And we'll go into why this is momentarily, but let's just make one more note under this table that K is ultimately unitless. K is unitless. Even though we can clearly see that units are going into these expressions, even if they don't seem to all cancel out properly, we will keep it unitless, and that's because there are these other aspects of the K expression called activity coefficients that wind up canceling all the units for us. But again, that's more of a PChem idea, so for now we'll just go with this rule. K is unitless. And so the reason why we say that K is unitless, even though I just went over the units that go into the K expression, is because there are these other parameters called activity coefficients that we're not bothering to include in this class. That's, once more of a PChem idea. But if you were to include them, they would cancel all the units always. And so just understand that even though it might look sometimes like, oh, there should be units, no. As long as we put in molarities for aqueous and bars for gas, and we don't include solids and liquids, we just report that number and we know by default what those units must have been. Now, why are solids and liquids not included in the K expression? Well, that's because their concentrations do not change as the reaction proceeds. And that's something you may remember hearing before, but may not be too clear on what that means. So let's try to understand it with a visual. So here we're going to contrast the gas versus an aqueous versus a solid or liquid species. Let's start with a gas. Imagine we have a container of 4 liters volume and 8 moles of gas in that container, thus we have 2 moles per liter. And then a reaction happens and that gas goes down by 4 moles. And so our volume of the container is still 4 liters, but our moles has gone down to 4, and thus our concentration has gone from 2 to 1. In other words, the concentration of the gas has changed upon reacting. And if the concentration of the gas has gone down by half, the pressure has as well. And that's just from basic Gen Chem gas laws, which we're not going to go over again, but that is why the concentration of a gas in these K expressions is expressed in terms of pressure, because pressure is directly related to concentration. Okay, let's look at an aqueous species. So now, still using that 4-liter container, but let's say the solution in the container is only 2 liters. Well, that's all that matters for an aqueous species. So let's say we have 8 moles in this 2-liter solution. So in other words, we have 4 moles per liter as our concentration. Once again, let's say 4 of those moles react, and we're left with 4 moles, but still swimming in this volume of 2 liters. And so the concentration has gone down to 2 moles per liter. Once again, our concentration has changed as the reaction proceeds. And now, solids and liquids work differently because they are so dense that their volume and their objective amounts, in other words, moles, which we can also relate to mass, but their volume and objective amounts are directly linked to each other. So let's say we have this very dense solid here, 8 moles in this tiny volume of 0.140 liters. If we do the math, we find that's 57.1 moles per liter. And now, let's react 4 moles. Well, we've lost 4 moles, but we've also lost half of the volume, because again, those two quantities are directly linked in these dense solids and liquids. And so our volume has gone from 0.140 to 0.070. And when I take that number and divide it by that, I get the same concentration as before. The difference between solids and liquids versus gas and aqueous species is with solids and liquids, the volume is determined by the amount of the solid or the liquid itself. Whereas with gas and aqueous species, the volume is determined by something that is independent of the amount. It's determined by either the volume of the container, which isn't changing, or the volume of the solution, which is not really changing either with this reaction. Very different situation with the solids and liquids. And so the biggest misconception that students take from this is that solids and liquids don't do anything in the equilibrium reaction. That is completely wrong. That was supposed to be an X. It is wrong. We see here, things are happening. We are losing solid. There is a reaction. It's just that the concentration is staying the same because we lose the same fraction of volume as we do of moles. And so that ratio of moles to volume is staying the same. So one more time, I cannot emphasize this enough, and it'll keep showing up for the next couple of lectures. Solids and liquids absolutely do participate in reaction, and their amounts absolutely do change. It's just the ratio between amount to volume, in other words the concentration, does not change. And the point of a K expression is to ultimately tell us what are our final concentrations after the reaction is done and equilibrium is reached. In the case of the solids and liquids, it's not interesting at all, because whatever it is at the end, it's the same as what it was at the beginning. So it's not interesting. We use the K to tell us about how these species change concentrations at the end of the reaction when we've reached equilibrium. And so this is where I would do a clicker, but we'll do it in Zoom. You're welcome to pause the video and try to do this on your own right now, or you can just wait till the Zoom session. So let's just move on to one last quick slide, which is the significance of K size. And what I'm about to say are really rough estimates, but typically, if your K value is greater than 1, then you will have more products at equilibrium than you have reactants left over. So we say equilibrium favors the product side. If it's less than 1, then equilibrium favors the reactant side. And if it's way less than 1, like 10 to the minus 10 or smaller, it's like the forward reaction essentially doesn't even happen, and you just still have all reactants. Whereas when K is much greater than 10 to the positive 10th, it's like the reaction has essentially gone to completion. You have no reactants left over, or it's a very negligible quantity. And that's when we represent the reaction the way you would at the start of a Gen Chem class, just with a forward arrow, representing the backwards barely happens. It's also worth noting that the size of K tells us nothing about the speed of the reaction. There is a giant K value with regards to the reaction of us combusting with the oxygen in the environment right now. It is very thermodynamically favorable for the universe for us all to just burst into flames. Thankfully, that reaction is basically impossibly slow, and that's because there's this giant activation barrier that makes it very unlikely for this reaction to occur. But if it did start, it keeps going, right? We intuitively understand that because it is very thermodynamically favorable.